Nothing beats. We're venturing on. And in this video, all of our previous conversations about limits leads up to this discussion about a topic called continuity. So we're going to introduce the topic of continuity in this video. Let's take a look here. All right. To help get across the idea of continuity, we are going to, in this example, investigate several different functions. And what we'd like to do is investigate the following functions' behavior, in particular at the location of x is equal to 0. So focus in on x is 0 for each of the following functions. So each of these functions, we're going to have the rule. We're also going to have the graph given, just like so in this first part, part A. F of x is equal to 1 divided by x squared here. You can see the graph as well on the screen. And so remember, our job is to figure out what's going on at x is equal to 0. X is equal to 0, of course, is just the same as the y-axis. Right there. X is 0. Now, what's going on? What's the function behaving like? Well, you can see graphically, clearly, this function is not defined at x is 0. And in fact, if you go to the function rule, f of x here, which is equal to 1 divided by x squared, if I were to plug 0 into the value of x, I would get 1 divided by 0 undefined, right? So first thing we should note is f0 is undefined. So it's kind of a problem spot to begin with, right? Moreover, though, it does have further behavior. Notice that this function on the graph, as I get close to x is 0 from the left of 0, it's blown up to infinity, right? So I'm approaching x is 0 from the left, and this function going straight up to infinity. Likewise, if I approach x is 0 from the right here, x goes to 0 from the right, function is also going up to infinity. So for that reason, we could also say that the limit as x goes to 0, really from both sides here, of the function f of x is equal to infinity. Noting that when a function blows up like it does right now, it's going to infinity from the left and that's actually from the right as well. Well, that is an example of a vertical asymptote of the function, right? The limit also doesn't exist. So in this case, right, this limit does not exist. So that one was kind of messed up, has some problems at 0. But let's look at another function. Now, all of this is supposed to lead up to the idea of continuity. Now, in this second function here, part B, we're given the function g of x, which is equal to the absolute value of x, but for non-zero x. So the graph that we see here given to us dictates this, well, right here at x is 0, notice there's a hole. We're not defined there because this function is only defined to be the absolute value of x for non-zero x. However, elsewhere, it's just behaving like it usually does, right? So in this case, we can note that again, if I were to plug in 0 into the input value, it doesn't have value, right? Because it's only defined for non-zero x. Hence, g of 0 is undefined for that reason. However, this graph does differ from the last one we looked at because now, as we let x get close to 0 from both the left and right hand side of 0, we can see that this function indeed is approaching 0. So we can write limit x goes to 0 of the function is 0. And it exists, right? Compared to the last one, limit didn't exist and it was undefined. In this case, the limit exists and it's undefined. So another thing that's happening for a function. Look at a couple more functions here that kind of lead us up to the point of what continuity is. Now notice here this function h of x in part C, very similar to the last one, it's going to be equal to the absolute value of x for values of x that are non-zero. However, this time, we actually do define it at 0, and that is h of x is going to be equal to -1 if x actually is equal to 0. Right here on the graph, right? The previous one didn't have that. Otherwise, it's the same graph as the previous function. Now, because this function is defined at 0 to be -1, well, h of 0 is -1 here. So here's the first one we've seen so far where the function is defined at x is 0. What about what's going on with the limit behavior at 0? Same as the previous one, right? As x gets really close to 0 from the left and from the right, the function is approaching 0. Limit x goes to 0 of this function h of x equal to 0. However, one thing to note, and this is kind of leading us up to the idea of continuity, is that there still seems to be a problem spot there, right? Because the function is defined at 0. However, this is like this removable discontinuity that just jumps down here. And so what we want to note is that the value of the function at 0 is actually not equal to the limit as x goes to 0 of the function. Even though each of them exist individually, they're not equal to each other, and we can see their behavior in the graph. There's this kind of problem spot, if you will, there. Now, last function, excuse me, before we define continuity is just k of x here is x squared. And we can see the parabola graph given to us right on the screen. Now, this one looks pretty nice, right? The graph is nice. There doesn't seem to be any jumps or holes or vertical asymptotes and that kind of stuff. So we note that, well, k of 0 is defined, right? 0. If I plug in 0 to x squared, 0 squared is 0. Also, notice, again, as I approach x is 0 from both the left and the right, this function is approaching 0. So we could also write the limit as x goes to 0 of x squared, this function k of x, is 0. And in this case, notice k of 0 is equal to the limit as x goes to 0 of x squared. They're both 0. Now, this right here, part D, is an example of a function behaving quote-unquote nicely, if you will. We call that continuity. And so we can see there's certain things that need to be satisfied in order for that to happen. We need the function to be defined there. Right? We saw that if it was not defined, go back up here, even like so, if it wasn't defined, there's this problem spot. There's like the hole in the graph, if you will, even though the limit existed at the same location. But not only do we need it to be defined, but we need it to be the same output as the limit itself, assuming the limit exists. Because like in this example in part C, we saw that, well, the limit existed at 0, but it was not equal to the output value of the function at 0. So there's still that problem spot. And so in like this part D that we just looked at, they matched up. The output value of the function, which is 0, right there, same thing as the limit of the function. When those two things both exist and match up, nice behavior happens. And so that tells us that we're going to define what the continuity at a point is for a function. And here's the definition right down here. Continuity of a function right now at a point, one specific location. So if a function f of x, we say that it's continuous at the x location, x is equal to a, if the limit as x goes to a of the function f of x is equal to the actual numerical value of the function at a, f of a. Those two things are the same. Those two quantities, we say the function is continuous at the location x is equal to a. In our previous example, when we looked at y is equal to x squared, that was true if a was equal to 0 in that case, at particular location. Now, functions don't need to be continuous at a location, right? And we saw a few examples just here priorly, but if it ends up that the function is not continuous at x is a, then we say that the function is discontinuous at x is a. So that's just, a vocabulary word. You may hear it mentioned. Discontinuous, the same as saying not continuous. So really, what do we need? Okay, when we say that, okay, if f of x is continuous at some location x is a, then we need this statement to happen, right? Limit as x goes to a of f of x has to be equal to f of a. The limit of the value of the function has to be equal to the output value of the function at location. But when we say that, we're actually saying, it's equivalent to saying simultaneously all of the following three conditions. And that is, well, you can't make that statement unless the function is defined at x is a, right? So first things first, f of a needs to be defined. Moreover, you can't make that statement either unless you have that the limit as x goes to a of the function f of x actually exists, right? So the function needs to be defined at x is a. The limit of the function as x goes to a has to exist. And even if we have those two things, still might not be continuous at x is a. And that's why we say, well, those two quantities should be equal to each other, right? So we got to go through this checklist here, make sure all three statements are satisfied at x is a. And if so, then we can conclude that the function is continuous at x is equal to a. So what we're going to do to wrap up this video is we're going to look at a graph of a function and just be able to kind of initially here in this first video on continuity, like, given a graph, can we identify the locations for which the function is discontinuous? And then state specifically why it's discontinuous. So that's what we're doing here. We're going to be given a graph of function f of x below. Specifically, we're looking at the open interval 0 to 5. And on that open interval, we'd like to identify any values of x for which the function f of x has a discontinuity and state the reasons why for each of these locations. Here's our graph. So it's kind of a funky looking graph here, piecewise defined. However, it's to get the point across, right? So again, we are only considering values of x on the open interval 0 to 5 here. Okay. Later on in another video, we're going to look at endpoints and intervals for continuity and whatnot. But right now, let's just think of everything in between 0 and 5 and not including the endpoints. So if we just look at the graph, right, the whole point is travel along the graph. If I start at x is 0 right after it, la-da-da-da, yeah, everything's nice. And then I get to that problem spot right there, right? Well, there's a location for which x has a discontinuity. So let's just make this list. X values for which f of x is discontinuous. Again, over this interval, right, 0 to 5. All right, well, first one is going to be x is 1. Now, why so? Well, we notice that at x is 1, the function is defined there by that dot, right? So that's good. F of 1 is 2. Check 1. Check 2. If I approach x is 1 from the left and from the right, limit exists. So we can see here that, okay, f of 1 is equal to 2. Limit as x goes to 1 of the function is actually equal to 1, right? as we just showed in the graph. However, they're not the same, right? F of 1 is not the same as the limit as x goes to 1 of f of x. And even though we had 2 out of 3 check marks marked from our criteria, the third one didn't match out, right? So hence, at x is 1, the function f of x is discontinuous here. Now you keep traveling along from x is 1, and we get to 3, we see another problem spot, right? Now, focusing in on x is 3, another discontinuity, we can see that the function indeed, again, is defined. It's that location right there, right? F of 3 is equal to 4. F of 3 is 4. But what about the limit as x goes to 3? Well, we notice that as x goes to 3 from the left, the function approaches the output value of 3. But as x goes to 3 from the right, the function approaches the output value of 4. So in this case, because the left-hand and right-hand limits don't match up, we can conclude that the limit as x goes to 3 of this function f of x does not exist. So that criteria is not satisfied. The end. Right? All we need is one of them to not be satisfied, and you are not going to be continuous at that location. Finally, keep moving along the graph. How am I going to get from here to here? There's the big old jump, right? There's our vertical asymptote at x is equal to 4. And in fact, in that case, at x is 4, we also have a discontinuity for a variety of reasons. One thing is that the value of the function at 4 is not even defined, right? It's undefined. So the end, right? We're discontinuous. However, we also note that even though as x goes to 4 from the left and the right, the function approaches negative infinity, limit doesn't actually exist, right? So limit x goes to 4 of this function does not exist. So that thing just has a whole bunch of problems going on right there. And there you go. There is an example of how function can be discontinuous at specific locations in a variety of ways. So let's go ahead and take a look at one last example here before we finish the video, okay? And that is this example right here. We're going to use the definition of continuity to determine whether each of the following functions are continuous at the specified locations. So in the first part, we have function f of x, this rational function here, 2x squared plus 3x plus 1 divided by x squared plus 5x. So what we're doing in this example is trying to show, like, okay, we don't have the graph given, right? We just have this function, and we have a specific location. Does it meet the criteria to be continuous at the specified location? In this case, f of x, and at x is equal to -5. So we got to go through our checklists, right? So remember the checks. Checks need all of these things to be true. F of, in this case, -5, but I'll just write a, f of a is defined. Limit x goes to a of the function exists. And of course, those two things, f of a and its limit as x goes to a of the function f of x, should be equal. So we just start with one of the checks, right? I mean, if one of them don't match up, then end of story. So let's check it out. What's going on with f of -5? That might be the first thing to check with. Is the function even defined there? Right. So let's plug it in. 2 times -5 squared in the numerator plus a 3 times a -5 plus a 1, all divided by, all right, -5 squared plus 5 times -5. Now top, we got a 2 times a 25 minus a 15 plus 1, so we can see the numerator is just some real number. But in the denominator, we got 25 minus 25. So what do we get? 50 minus 15 plus 1 over 0. This function is not even defined at -5. So f of -5 is undefined. And hence, what's our conclusion? We're supposed to use the definition? Well, I just did. Because all I did was check out whether the function is defined or not. And it's not at this location. And hence, f is, as we say, discontinuous at x is equal to -5. Bam. How about the last part, this last example? Again, we're going to use the limit definition of continuity here. And in this case, we're given a function g of x, which is a piecewise defined function. It is going to be equal to x squared minus 4x plus 3 over x minus 3 if x is not equal to 3. And it's going to be equal to 2 if x is equal to 3. And it's kind of weird looking, but it's supposed to be kind of like a comma right there. Our job is to investigate what's going on at this location. X is equal to 3. Okay. Well, let's go through our checklist again. All right. First things first. G of 3. Is it defined? Sure is. This function is defined to be 2 when x is 3. So it's 2. Boom. First check. How about limit? Limit x goes to 3 of g of x. Does it exist? Well, it's the same as the limit as x goes to 3 of x squared minus 4x plus 3 over x minus 3, right? Because as long as we're arbitrarily close to 3, that's what the limit definition means. Now here, even though we see that the denominator goes to 0 when x goes to 3, let's go ahead and factor the numerator here. Notice it factors to x minus 3 times the x minus 1. And of course, all divided by x minus 3. So x minus 3's cancel. This is the same as the limit as x goes to 3 of x minus 1, which is just 3 minus 1, which is 2. So limit exists, right? From previous algebraic methods that all worked out. Now you see g of 3 is equal to the limit as x goes to 3 of g of x. They're both equal to 2, right? Bam, bam. All three checks are checked. Thus, g of x is continuous at x is equal to 3. Right, so, I mean, that's the video basically, but the whole idea, define continuity, kind of where does it come from, and then look at an example graphically, and then look at a couple of examples using their formulas that we've been given. Go through the checklist. So we're not done with continuity. The next couple of videos can be focused on continuity, and that's just the introduction to it. So hopefully it gives you a better understanding of continuity, and that's Math and Beats, and that's the end. So later.